to Module 14 on bias variance trade-off and on learning curves. So recently you learned how to measure performance of in regression and in classification. You also learned how to estimate those metrics reliably. So we saw that different splits of the data can result in very different performance. So we tried to overcome that challenge by using cross-validation. An idea that's going to come into Module 14, coming from Module 13 in cross-validation, is that different data sets will produce different models, and those models will perform differently on the data. So like the sample that we're using and the model that we're using are both somewhat random variables, and therefore their effect on performance will be variable. And today, the bias variance trade-off will be about sort of quantifying or even just qualifying, like understanding subjectively how models learn on different sets of data and what their overall behavior tends to be, like how consistent they are, essentially. We're going to be talking about model complexity and regularization. This is actually going to be topics we'll get into explicitly in greater detail later, but today is going to be partially just about understanding the trade-offs that we have to deal with, but then that feeds into future modules. So just to orient us, consider the idea that we can get a model that will actually get worse as it gets better, right? The idea here is that a model gets better if it gets richer, if it has more parameters, more dials to learn when it's training. And on training data anyway, the training error is going to drop like a lot. So it's going to get better. It's going to be a better representation of the training data. But when we look at held out validation data, either in a validation set or a test set, then error will, at some point anyway, rise. And then the whole model that appears to be getting better and better in one context suddenly gets worse in another. And again, this reemphasizes the idea that model performance is closely aligned to data. So here is a little example. Here's the code just for transparency's sake. There's not too much interesting going on here. What it does is it produces a true model, like the universe is this blue curve over here, this sine wave. I'm calling it F star. Throughout today's module, F star will be like the function that generates the data in the real world, like the true universal function that we don't have access to. We only have access to its samples. The red dots are training samples, and then the kind of turquoise X's are test samples. Just a quick comment, like obviously the ratio of training samples to test samples is off here. This is only for the point of demonstration. Normally we have way more training data points. And then as we, I'm going to basically change the size of the model. So down here we have the polynomial degree. We're going to try to fit a polynomial to the training data. And at first we have a polynomial of degree 0. That's just a straight line, which is sort of the average of all of our training points as y values. I'm just going to jump to polynomial of degree 1. Polynomial of degree 1 is just a straight line. It's linear. That's this turquoise line down here. So this is our model y hat. Usually y hat, anything with a hat on it, refers to like an estimate. So this is like the model's estimate. That's y hat. And then over here on the right is going to be two different metrics. We're dealing with mean squared error. This is a regression task, so we're doing mean squared error. In the purple curve is our mean squared error on the training data. And it's going to be very low, so we're going to do a very good job of fitting the training data with all of our polynomials. But the orange curve is how well we perform on the test data, all of these test samples over here. Which again, like the training data and the test data generally follow this curve, so more or less they look similar enough to the reality that we should be satisfied, but we'll see as we make our models very big. You can see it already, like the mean squared error on the test data will jump crazily. Let's go ahead and play this, so you'll see as we move the turquoise model will get more and more complicated. So I'm going up to degree 6, and already at degree 8, actually I think at degree 7, we've got to the point where the mean squared error on the test will actually get worse and worse and worse, at least for a time, right? So you can kind of see this now. Look at the turquoise curve. And look how crazy it's getting as the model's getting more advanced. So like right now you can see that the model, this model with a high degree, it's a very complex, this is an 18, this is like x to the power of 18 plus x to the power of 17 and so on. It's a pretty complicated model with lots of relatively many parameters. You can see how well this model fits all the training data. The turquoise curve goes through all these points. So the training data, so the training MSE is very, very low. This green dot over here actually shows you where we are now with the MSE on the test data. So like how well are we predicting all of these test data samples? Well, pretty poorly. In fact, the worst case here is polynomial degree 16. You see, so we do a very good job fitting the training data, but because the model suddenly like tries to fit the training data so much, a bit of a spoiler alert, it overfits on the training data, and then therefore does very bad when we try to see if it generalizes. You know, this could be a bug or it could be a reality. So like we want to delay like being too certain about anything until we get enough experimentation. So it's always possible that we get changes to MSE in our validation set that is reasonable, and it's not just a bug in what we're doing, but here it kind of is a bug. We've decided to make the polynomial too complicated, and therefore it's very bad at predicting the test data or the validation data. Okay. If it's a law, like if it's something that we've actually like need to change, then we actually have some possible things we can change. We can change the capacity. We can potentially get more data or modify the data in some way, or we can do regularization, which is the subject of a future module after this one. So by the end of today's module, you should be able to derive the bias variance decomposition, at least in high-level terms, like describe what like the overall error is built out of these three different components. You'll be able to diagnose underfitting and overfitting using learning curves. We saw an example of overfitting at the end, but also some of the early, like the straight line curves through our data was too simple, and that's an example of underfitting. You'll be able to decide whether you need to add data, whether you need to regularize, or whether you need to change the entire category of model. And then you'll also be able to connect ideas from today to previous ideas from previous modules. So again, getting back to the conceptual scaffold, where we're starting from, we have a trained model, f hat, which is a function of a data set D. Remember before we talked about how like different folds in a cross-validation setup will have different performances. The parameters will be set differently because the data sets are different. So in some sense, the model F is a function of the data set, and if D is random, therefore F hat will also be random. The performance will be a bit over the place. So two expectations we need to keep straight. There's expectations over data points, like what do we expect to draw from a data set? This is X and Y, like this is like our inputs and our outputs derived from a data set D. This we can compute expectations on. Like the expected value of X is this, the expected value of Y is that. That's how we've been conceiving of expected values or averages before. We also need to consider expectations over training data sets. So we have a lot of different data sets. Every data set will produce a slightly different model, like the parameters will be slightly different. And we want to consider, out of all of those different data set and function or model pairs, like what is our expected model, right? So a bunch of different data sets produces a bunch of different models. Those different models have different behaviors. What is the average of those behaviors? What is the expected value of those behaviors? So the bias variance trade-off, or the topic of today's module, is about decomposing any kind of expected error when we're making predictions into different parts. And these parts will be based on the randomness in the data itself, and the noise in the data itself, but also over the different possible samples we could have taken. That is to say, there's going to be some kind of error associated with the sampling of data sets over the sampling of models. So I'm going to show you a couple of ways of looking at the same thing, these three sources of error. So what this graph is showing is like the Y value is something we're trying to predict through a regression. And imagine we have some fixed value of X. So there's a particular data point X in our test set, and we're trying to make a prediction of it based on a model. The actual observations we have come from the model of the real universe, the true model, which we call F star. You can remember it because it's a star. It's the best one. You know, it's F star is the universe. So the universe has this model F star of X, but it also has a little bit of noise, right? Maybe, I mean, we don't have to get into detail, but there's something about the universe which just creates some randomness. So the observations are never going to be exactly the same from sample to sample, and that's represented by more or less like the different heights of these X's. These are the observations that we'd observe from the real world. So F star over here represents the real world, and then the noise, this kind of distribution here I'm showing on the left over here, is this the variance of the observations y, which I've indicated as orange x's. Now, all of these blue dots represent different possible models we could have produced on slightly different distributions of training data, right before we looked at X over here. So we had different data sets, very similar but different samples, different folds, whatever the case is, that produce different models. And then given a particular X, different models will make different predictions. Those predictions are shown by these blue dots. And as you can see, these like actual real models that we've built will produce a variety of predictions. So the expected value over all of these models, all these different models for the same X is producing different estimates. The expected value over all of the data sets I've had for the model I've produced is indicated here, this blue dashed line. It's like the average of all my models. And then the variance is going to be the spread of my prediction. So y hat is a prediction of model f hat. So the variance is more or less like this is the spread of predictions. Okay, so this is pretty straightforward. There's a little bit of noise caused by the universe itself, which is our actual noise. And then there's this variance, which is caused by the fact that I'm using a bunch of different models for making predictions on the same value of x. So again, F star is the ideal predictor because it's the actual model of the universe. We're trying to approximate it using our models. If we had a perfect model, we'd have a perfect classifier, or I guess in this case, rather, it's a perfect regressor. But we don't. We have just estimates, which are these blue dots. So again, a moment ago, I defined like our samples y coming from the model of the universe, F star, our ideal predictor, plus some noise, epsilon. Now, we're going to assume the expected value of epsilon is 0. That doesn't mean like I'm always going to get 0 error. Sometimes I'll get some positive error, sometimes I'll get some negative error, but on average that balances out to 0. The average error is 0. This isn't always the case, but it just simplifies how we talk about things now. So now I want to talk about the bias and the variance, which we kind of saw a moment ago. And here's a more explicit way of looking at it, and then I'll show you another picture which again tells the same story. Bias, it basically tells you like how far away the average is of all of your experimental models, how far away they are on average from the truth. Here it is, right? So here's the true model, F star. What is the difference between F star and our average model? So the expected value of our produced models is like the average model by definition. So the expected model makes some prediction, like there's an average prediction over all of these models. I have the actual prediction by my perfect reality model F star. There's some difference. That's my bias, right? All of these models are biased to this amount. But then I also have the variance of those predictions. Again, this is something that you probably know already from high school, but like the details here might trip you up a little bit, like where do I put the hats and everything. Here I'm looking at the expected value of the square difference of each of my models and the average of those models. So here is this first factor here, or the first term, I guess, is like each of my models, f hat. I take the difference of that model from, I take the difference of that model and the average over of all my models. So some models will be similar, the difference will be small. Some models will be very different than the average, the difference will be big. I square that difference. I take the average of all those square differences. That's my variance. Okay, that's by definition. That's kind of how variance is defined generally, as a quantity, as like the difference between a quantity and the average of that quantity squared. But here what we're looking at is models and their predictions. Conceptually, if that's too much for you, again, variance is a representation of spread, and the name variance also kind of means spread. It just represents like the variety of models over space. And then we have this irreducible noise. So we have the bias, which is the average of all of our models. We have the variance, which is the spread over all of our models, our experimental produced models. And then we have like the true error, the true noise from our model epsilon, and I'll call the variance of that sigma squared. So here's another visual of this, what we were talking about a moment ago. We haven't really talked about anything new. We just kind of plotted things out differently. We have a particular x again, so for a particular value of x and a lot of models. So now all of these blue dots represent a bunch of models. These orange dots also represent other models. All of these models were produced just by training on different subsets of the available data. The bias in each case is just the difference from the true value of what y should be, which is kind of hidden here, but this is like 0.8 is reality. This is what the best model would predict. On average, all of these blue models are making predictions quite a bit lower. Their average is quite low compared to the truth. So their bias, because we're dealing with the average, is big. In the orange case, the average of the predictions of all of these orange models is over here in this dashed line over here. This is the expected value of all of these produced models, f hat, for a particular observation x sub 0. And the average of all of these orange dots is actually pretty close to reality, right? So the bias is small. On the left, the bias is big because the average is far from the truth. And on the right, the bias is small because the average is close to the truth. That's one big component, is bias. And variance, as you can see here, just describes the spread of our observations. On left, all of these blue models, the spread of all of these blue models in terms of their predictions, it goes from 0.4 to about 0.64. So that's a pretty small difference. The variance is small. On the right, all of these models make all these different predictions. Those predictions go from 0.5 all the way to almost 1.1. That variance is relatively high. Again, on the left, we have a collection of models that have high bias, low variance. And on the right, we have a collection that is low bias, high variance. I should mention, again, that the high and lowness of these things are just positive quantities. So it doesn't matter that I'm underestimating my predictions. On the left, it's just the absolute difference is big. That's the positive high bias. Like the bias is large, is what I'm saying. So let's take this individual model. So we have all these possible models we can have trained from data. Let's look at just two kind of extreme cases. So here we have, again, the blue dots represent training data. The dashed line represents the true function f star. And then the orange models represent our models. So our first model is just a simple polynomial of degree 1. It's a straight line. And we fit it, and here is the fit. This is what we call an underfit, right? So the model here is too simple to capture the curve. The distance between the training data and the model is pretty big. This is not a good representation of the data. It's underfit. In this case, like the training error will be high because like look how far away we are from the truth, but also just because the test data generated by f star, generated by reality, will also more or less follow this sine wave. The predictions made by this orange model will also be pretty high, will also be off. So this is an example of high bias, low variance, in the sense that the predictions will be consistently wrong in the same way. I'd welcome you to go back to the example I showed you before with the slider and try to convince yourself of that in that way, or get some code and play around with it if you want. But when you have a model that's very simple like this, the predictions will tend to be off, but they'll be off in more or less the same way, in a more or less consistent, simple way, and it's consistent and simple because the model is consistent and simple. Overfitting is this other extreme case. Here we have a polynomial of degree 15. Here the model is too flexible. We have too many parameters that we can change for the data. So the training error is either almost zero, or as is the case seems to be here, is exactly zero. My model goes through all of my training points. But the validation error will end up going higher, right? So like look over here, for example. This is actually a relatively realistic view. You might see other like textbooks or other slides in which they overemphasize these differences in a non-realistic way. This is realistic. So most of the time, our model, our too complicated overfit model, fits the training data like fairly well, and it also fits reality fairly well. Here, there's only one little kind of hiccup where the model predicts something that is relatively far away from reality. So if it was going to sample more data from this dashed line from reality, they'll more or less follow this curve. Those new test samples will be far away from my orange model, and therefore my validation error will be bad. So in either case, validation error being bad is what we were trying to avoid in the first case. So here's an example of low bias, high variance. The predictions will on average, be pretty close to the truth, but they'll swing wildly. The variance will be crazy, right? Like sometimes the predictions will be like far lower than they should be or far higher than they should be. On average, everything balances out to being close to reality, but with these crazy swings. So overfitting refers to low bias, high variance. I'm going to show you just another graph in a second to make this difference between underfitting and overfitting simple. But I think high level, it is a simple idea. Underfitting just means you have a model that's too simple. It doesn't do a good job of representing the data. Overfitting is like the opposite. We've hyper-fixated on the training data with all of our parameters, and therefore we lack the ability to generalize. Here's that graph I mentioned earlier. This graph comes up in a couple of different sources, like the ones I've cited here. So here, the idea is X's are predictions made from a model on a different data set, like on a held out data set. So we have a model already, and now we're going to make predictions. The bullseye, like how close your predictions are to the center of this bullseye, is the truth, and that's what we're trying to predict. Obviously, we want most of our predictions to be pretty close to the truth. I mean, this is one reason why I don't necessarily like this image, because the truth is going to change all the time. Like the bullseye is going to be constantly changing based on, your X and Y, so the values will be different. But just for visualizing the relationship, this kind of makes sense. We're constantly making predictions. All of these predictions are represented by these X's. How far away are these X's from the truth? That's what these bullseyes are showing you. So what we would like is obviously this thing in the upper left-hand corner. Most of our predictions are just very close to the truth. Like on average, they're close to the truth, so the bias is low, and they're also very consistent. So there's not too much like crazy swings of the data. Even the furthest predictions we make away, the furthest away predictions are from the truth are still pretty tight. So the variance is small. You see? Look how small the spread is. Look how like overlapping the average of these X's are to the truth. In overfitting, like we mentioned a moment ago, on average, the model is making predictions that are, on average, close to the truth, but with crazy, wild swings in prediction. So the average of all of these predictions, all of these X's, is, I'm kind of putting it over here, like where my mouse is. So not that far from the truth. So the bias, the difference between the average of these X's and the truth is kind of small, so the bias is low. But the variance, as you can see, is much wider. Like sometimes I'm close, sometimes I'm far. It's all over the place. That's overfitting. Like I mentioned also a moment ago, models that are too simple will, on average, be quite wrong, but they'll be consistently wrong. So it'll be high bias, low variance. Here you can see the average of all of these predictions is quite far from the truth. So therefore the bias, this difference is high, but the spread of all these predictions is low. Low variance, this is underfitting. The worst thing we can possibly get is just like on average we're far away from the truth. We have high bias, and we also have these wide swings in our predictions. So the variance is high. This is the worst case scenario down here on the lower right. So our key result here is that the expected value of like the square difference between our predictions f hat and the truth y will be broken down into different forms of error. There'll be a bias term, there'll be a variance term, and then there'll be an irreducible like fact of nature, fact of life. Okay, so bias again is a systematic error, like it's systematically far away from the truth. Sensitivity will be like basically how consistent we are, and then there's the irreducible component. This right here is the classic bias variance decomposition of expected prediction error. You can read more about it here, for example. This is a textbook. I might actually link to some other web pages you can read more about this breakdown if you want to see the history of it. But again, the bias variance decomposition is just a decomposition of three terms: bias and variance, which we get from the title, and then this bit of error from nature itself. So again, just to hammer this home, bias is the average prediction being systematically off. So it's like the wrong shape, wrong assumptions, something of that nature. Variance means the prediction's jumping a lot when the training data changes, so like the modeling itself is very sensitive. And then noise is like even the perfect model can't beat the random flukes of the real world. So here's a bit of intuition. We're doing machine learning, so we want to fix things. We want to build models that are closer and closer to the truth. The good news is that we can fix bias and we can fix variance, and we'll slowly see that over a couple of modules. Some error we'll never fix, and that's fine, right? We're not logicians, although we use a lot of logic in machine learning. We're doing empirical science, which has to do with statistics, and there's always going to be a bit of background noise we have to contend with. This is a bit of a proof. This is an aside, so if you're studying for things, go ahead and skip this slide if you want. But for those of you who are so inclined, I wanted to just step through where this decomposition comes from. Okay, so I think it's a little bit interesting. And also, we're just going to skim over the surface of this proof, so it's not like a full, proper proof or anything, but it just sketches it out. So again, imagine X is fixed, we have some input, and we want to make a prediction. The perfect model, F star, will have some prediction, and then it'll have some world noise epsilon, this irreducible world noise epsilon. For now, again, we're assuming that on average, this error is going to balance out to 0. But that's not always the case, but it helps us just at the moment, just for this specific case. And then the expected value of the squared epsilon is, we call it sigma squared. This is going to be just the noise of the universe. Mu x is the expected value of the predictions of all of our produced empirical models f hat over all of the possible data sets we have at our disposal. Again, this is the average predictor over the data sets. So what we kind of want is this form, right? So the expected difference between the truth and our predictions, or rather the expected squared difference. We just defined it a moment ago. We want bias plus variance plus the universe's irreducible noise. Bias we've defined as sort of the distance between the true model, F star, and the average of all of our models. Remember the graph I showed before? All of the points I have, all those predictions, there's a specific average to those predictions of all of my empirical models. That's mu. What is the difference between the average of those empirical models and reality squared? That's my squared bias term by definition. And then the variance the variance is really just about the models. I don't care about the true model for the moment. I was looking at the spread. So just like every other variance, it's a distance between, or the expected distance, or the average distance, same thing, between each of the points I have available and the mean. So for all of my possible models, f hat, what is the difference between that model and the average of all my experimental models, which I defined over here a moment ago as mu? If the square difference, that's variance by definition. And then once again, noise is just the third term. So is this actually going to be the case? I'm actually going to get from this left-hand side to the right-hand side. Let's try ahead and do that. So I do know that what I want is on the left-hand side. So starting on the left-hand side, I can start rewriting things. Y is, by definition up here, it's the prediction made by the true model plus some noise from the environment, epsilon. So I just go down here and I plug in, I replace Y with this blue part over here, f star of x plus epsilon. This is Y by definition. That's all I've done so far. Now I kind of do a little trick. I kind of add the average predictor over data sets, mu, and I subtract it. So adding a quantity and subtracting the number, they balance out to 0. So it's like adding 0. So I haven't changed anything. I haven't changed the this quantity. The quantity being f star of x plus epsilon minus f hat of x. I haven't changed anything by just adding mu and subtracting mu. So this blue parts I add and subtract. Okay, so hopefully you can see how I'm not actually changing anything in terms of the quantity. But then I can kind of shuffle these things around. I can group them. So f star minus mu over here, and then I have mu minus f hat over there. Now, that's kind of it. So now, like, I've replaced this inner quantity for this expectation. This expectation is, behind the scenes, hidden to me right now, just a sum overall of my available models from all of my subsets of data, on average, so divided by the total number of subsets. So I have these three terms now, which I've kind of blocked off in terms of these parentheses. So what is the expected value of this entire thing? Well, it's the expected value of the first term plus the expected value of the second term plus the expected value of the third term. What is the expected value of f star of x minus mu of x? Well, that's by definition what I was looking for. What is the expected value of my average error over my models, and the like any of the individual models? The expected value of the squared difference, because sorry, remember I'm doing the squared over here, so this squared comes down over here, and it comes down over here also. This is the definition of variance I was looking for earlier, and I'm left with squared value of epsilon. Squared value of epsilon, which is my universal noise, is what I've previously also defined as over here as my universal noise. So, I mean, this is an aside, so like, if this isn't leaping out at you as being super interesting, like, that's fine. I just wanted to highlight how we get from, like, what we know to be what we're looking for, the difference between the truth and our models, and the expected difference between these things. We have taken definitions and split them off into terms, and then those terms ended up being exactly what we defined a moment ago. There's a bias term, there's a variance term, and there's a noise term. And those are all separate from each other. Okay, so this doesn't come from nowhere. This doesn't come from Hastie and Tibshirani and Friedman out of thin air, or their predecessors, obviously. It's a representation of reality. This is a true law of the nature of machine learning. Let's just do a tiny numerical sanity check just to make sure like everything is computable. So imagine we have some value of x. In reality, the prediction of x should be 2. So f star of x is 2. Now imagine we have a ton of data sets. All of these data sets produced different models. These models we call f hat of x. On average, all of these models predict 1.6. And then the standard deviation of the predictions of all of these different models is 0.5. And imagine somehow we know that the noise standard deviation is 0.3. Okay, so the bias, the squared bias, is just the difference between the average prediction and the truth squared. So 1.6 minus 2 squared is 0.16. The variance is the variance I only care about the spread of my predictions. The standard deviation of my predictions is 0.5. So the variance is just the square of the standard deviation. So 0.5 squared is 0.25. And then somehow I had access to the universe. I knew that the noise was 0.3. 0.3 squared is 0.09. So the expected squared error that I'm going to get, this is what I expect to see, like over a bunch of experiments, is going to be the squared bias, 0.16, plus the variance, 0.25, plus the noise, 0.09, which is 0.5. So if you're doing machine learning and you're producing all of these models, and you're producing some, you're understanding the bias, you're understanding the variance, and you can compute them, then you also know what the expected squared error is going to be on this collection of models. You can say something about like, this is the squared error I expect to see in total. So when I'm making predictions, like any new model that I produce on some other subset of data, I expect its error to be 0.5, right? And I know that because I have like the bias over all of the experiments I've done previously. I have the variance over all the experiments I've done previously. I have the inherent noise of the universe. So therefore, if I were to produce a new model now, under similar situations but using a different subset of data, we're going to expect the squared error to be 0.5. So just a quick anti-example. This is where this identity or this definition is not going to be literally true. This bias variance equation depends on several things. It depends on the fact that we're doing a squared loss. So I can talk about this squared difference between like the average prediction, y hat or f hat of x, and the truth. I can talk about the standard deviation between all of these predictions. All of those predictions, remember, were on a scale. I'm doing regression. The examples I showed of overfitting and underfitting was doing regression. So we're doing mean squared error and we're predicting continuous values. So I assumed a squared loss. If you're doing classification of many types, where we're doing this like nominal categorization, then the algebra, like the breakdown we did a moment ago, would fail. There's other alternatives to doing bias and variance using classifiers, obviously, but we haven't seen that yet. If we're not doing like IID sampling, so if we're using a time series in which like an observation at one time actually depends on what we observed previously and there's some relationship between data points, then this also breaks down a little bit. We keep on assuming that all of these samples are independent and identically distributed, but it's not always going to be the case. And we also assumed finite variance. Sometimes finite variance noise. So sometimes the noise itself can fluctuate in ways that aren't as predictable as we've kind of laid it out so far. So the way we kind of tend to frame things in a modern sense in machine learning is that the decomposition that we talked about before, bias and variance, will still guide our interventions. Like the same problems that produced underfitting and overfitting before with a simple regression case actually generalize very well. They generalize very well to very complicated transformer neural networks on much more complicated data. So this idea of how much data we have, how much capacity we have in terms of all of our parameters. Also regularization, again, which we're going to see in a module coming up. All of that still applies, whether we're doing simple regression or fancy neural networks. There's still the conception of bias and there's still the conception of variance. It's just that we wouldn't write it down on paper like we did a few moments ago. So let's do a couple more examples, just to hammer things home a little bit more. We have a true model. So f star is the sine of 2 pi of x. And then we have our universal background noise epsilon. Epsilon is drawn from a normal distribution with mean 0 and variance 0.1 squared. The standard deviation is 0.1. And we're going to fit polynomials of degree 1, 3, 5, and 9 on data that we sample from this process. Okay? Here's the code for you to download and play around with. Nothing much more is happening here that we haven't seen before. Generating data comes from here. Here's my sine wave that I just mentioned a moment ago, 2 pi x. There's a little bit of normal noise over here. So here's our zero mean. Our noise is provided to us, which is 0.1. Anyway, everything I just mentioned a moment ago is here. And we're going to fit a polynomial. So the polynomials come from, in this case, NumPy. We're using the NumPy library to fit polynomials to our data, x train and y train and so on. Okay, so nothing really fancy is going on here. I think I can turn some off. Yeah, there you go. So I have my my true model, which is this red line. This is f star of x. All of these blue dots are my samples, my training data. I fit a polynomial of degree 1. It's a straight line. That's this downward shaped thing over here. You should know by now whether this is underfitting or overfitting. You might even know right now if this is going to have a high bias or a low bias and a high variance or a low variance. And then I fit polynomials of degree 3, 5, and 9. And right away you can see that these nonlinear functions are fitting the data a lot nicer. Okay, so nothing much more to say, but you can kind of see also here, I can scroll down and I can see what the prediction would be for each of my curves if a particular value of x is provided. So, I mean, this is reality. So again, like in cartoon examples in textbooks, they'll go to polynomial degree 9 for a small amount of training data, and they'll show a polynomial that's fluctuating all over the place. And what they're not going to tell you is that what they've actually done is they've tweaked these polynomials to emphasize errors, and we're not doing that here. But you can already see that some of these polynomials of higher degree, so the purple curves, the orange curves, the turquoise curves are making predictions that are starting to fluctuate kind of wildly away from the truth in red. So, like, just saying something looks wiggly, looking at a prediction and saying it looks a bit wiggly, like that's not going to be enough to convince your colleagues when you're doing machine learning in practice. So you need to have some diagnosis, you need to do science, you need to have a hypothesis that you can try to disprove. So your hypothesis might be that what's happening now with these high degree polynomials is this overfitting. So therefore it's going to be, if something's overfitting, it's low bias. So on average, the error is small, but the predictions being made are wiggly. They're kind of all over the place. The variance is high. So our test in that case, if our hypothesis is overfitting, is we'll add more data or do more testing. We'll increase regularization. I'm sorry to keep on looking into the future here, but this is like what we would do is regularization to kind of fix that variance. Because if variance is the problem, then we want to reduce the model's like freedom, so to speak, to chase noise. We want to keep it tight and constrained. So again, adding some regularization to constrain things is the subject of a future module, or adding more data so that any inherent noise in the universe won't be chased by the modeling process, which is kind of what's happening. Then if we solve that problem by doing this intervention, then that's an indication that, yeah, indeed, this might have been overfitting. If the hypothesis is that our model is underfitting, remember underfitting is the variance is small but the bias is high, then, well, we simply might use a richer model. We might weaken regularization. Again, come back after you've seen the regularization module. So, if bias is dominating, if most of the error we're observing comes from the fact that we're very biased on all of our models and in the predictions of those models, then more flexibility should help us lower the training error and lower the validation error, at least initially. So all of those points which are way off will gravitate towards the truth if we have a model that can do more. And if we observe that, then that kind of confirms to some extent our hypothesis. And then if the hypothesis is that we have some evaluation bug or there's some leakage going on, like we haven't done cross-validation properly, then you go back, run validation properly, maybe shuffle labels, maybe rerun the pipeline, maybe leave one out, cross-validation, do the careful empirical work to make sure everything's set up properly, just do the debugging work. One thing I should mention, when I said shuffle labels, I don't mean like shuffling the data points. I mean actually taking the data points and just changing the labels, right? So the ground truth was Y, but imagine if I just like change Y randomly and make the predictions totally random. If Y is totally random and there's no signal for me to find because like I'm predicting nothing, I'm predicting pure noise because I've shuffled my labels to be totally random, then every model should basically be random. No model should beat chance. What constitutes beating chance is a question for statistical significance testing, but hopefully you get the idea. So if you happen to get a good result, if you happen to get a result that like you've trained a model and it's getting very high performance, like it's getting very small mean squared error, then you could be like, well, look, something crazy is happening. Like there's no signal here. There's nothing to learn. A model that is getting great performance when there's nothing to learn because I've changed the predictions means that like something bad's going on. I'm not saying someone's cheating, but that's also something that could have come up. So let's estimate our variance empirically. We can sample a bunch of training data sets. We can refit, and we can look at prediction spread. So here's our code. We have different degrees, 1, 3, and 9. And I'm calling this estimate bias variance. I have 30, you can pass over very many you want, training samples, but I'm going to say I want 30 samples, I want a degree. Here I'm passing the degree in this loop. I go from degree 1, 3, and 9. The default is just going to be 9. I can do a bunch of repetitions, and then I have this universal noise, which is 0.1. Again, I'm only estimating bias and variance, so right now, for the sake of argument, I have access to the truth. I have F star, so I know what the data should look like. For underscore in range, this is a curiosity of Python. Underscore basically is an unnamed variable, but it's just basically saying, for every repetition. So like I don't care about the index. I'm not indexing over a bunch of elements of an array or anything like that. Just do the following thing n reps times, in this case 200. So generate some data, which I think we defined in a previous cell. Add some noise to it. That'll give me my x's and y's. Okay, and then make a prediction. I also defined this in a previous slide. I make a prediction and just keep on appending the predictions to the end of my predictions list, preds. Initially it's empty, and then 200 times I'll generate some data, like a totally new sample of data. I'll fit a polynomial of degree d to those data, and then make my predictions and then store them. Anyway, I'm getting into the weeds a bit. I didn't mean to do this. Everything we've seen here, we've seen previously, so you can download it and play around with it. Anyway, so we have our models of degree 1, 3, and 9, and we have 200 samples of different samples of data. We've made models for each of these samples of data, and then therefore we can compute biases over those 200 data points. Just to make sure 200 is always consistent. Yeah, so I do 200. So I passed 200 even though it was the default anyway. Anyway, I do 200 iterations. I have 200 models now making predictions of degree 1. They have an average. The square difference between that average and the truth is about 0.2. And they also have a variance over all of those predictions. That's 0.017544. Okay. Actually, you're not saying anything too surprising here, but this does actually fit our description from a few moments ago very well. Partially luckily, but what else do we expect from just doing experiments of this type? So a low degree model is one that should underfit. That's one that's going to be consistent, but it's going to be consistently wrong. So we expect the variance to be pretty small, and it is. We expect the bias to be pretty big, and relatively it is. And so everything kind of lines up. On degree 9, this is where we have a model that might be starting to overfit. So on average, the predictions made by this too complex overfitting model will be small. The bias will be small, and indeed it is. But the variance will be pretty high, and indeed it is. So the predictions made by this model will fluctuate wildly, so our variance is very high. And everything kind of lines up. And here in the middle is our ideal situation. Remember we had in the, it was at the upper right-hand corner, I think it was, where the bias is small and the variance is small. This is the model we like. And this one, like on average, like, we have 200 models of degree 3 now, but degree 3 was a good choice. Here's just another representation of the same thing. We have the polynomial degree. We only have 3 samples here, but you can see the bias term and the variance term are the blue and orange curves respectively, and then the total error is sort of a combination of these 2 things plus the inherent noise in the universe. I would recommend to you to go in here, and you have all the code available to you, so go in here, download this, change the degrees to other things, change it to 5, 7, 9, fill out the space a bit more so it's a bit less crude looking, and then just see what happens to these curves. So speaking of these curves, let's look at the overall training curves for training error and test error. We're going to do 2 different things now. We're going to change the amount of training data we have available, which you could have changed in the previous code a moment ago. And we'll also change the number of parameters we have, which is like if we're doing a polynomial, this model is just the degree of that polynomial. So this is actually like sampled from real data. Like this isn't just an image. This is like hidden behind the scenes. I've used Python to generate these. On the left, we're adding more and more data. And the more data we add, we observe that the training error rather, and the test error end up going down. Right? So the more information you've extracted from the world, the better your predictions are. Right? Like first of all, you do a better job training, but also you've seen more of the kind of variance that occurs in the real world. So therefore, you make better predictions on future data, which is held here in the test set. So generally, that's good. More data, the better, always. On the right, we have our number of parameters challenge, like the complexity of the model challenge. So here, we saw the very first kind of interactive thing before. We can keep on decreasing the training error, so we can get better and better on training data. But as the model gets more complex, at first we start fitting the data and the test set better and better. But at some point, we end up with a model that is overfit. it's going to start making wild predictions, and then the test error goes up at the end here. And we don't like that, right? The test error going up is the thing we don't like. So this is the observed from data, but it's something, yeah, it's observed from data, but it also matches our expectations. If we increase the model complexity, the training error will generally keep dropping, but the test error will be U-shaped. Okay? So underfitting is bad, error is too high. Overfitting is bad, error is too high. But right in the middle is a sweet spot where the error is small. And again, I don't need to hammer this home anymore, I don't think, but usually we won't have access to the true test data, so you can't change the number of parameters until you get to the sweet spot over here and say, here's our model. But you do have validation data. So remember, you have training, validation, and test. So you can take the training data, you can train a model of degree 1, 3, 5, 10, whatever you want, and then keep on evaluating them on the temporarily held out validation set. And then the validation set will act as if it's a test set, and you'll see a curve like this. And at some point, you'll see, well, for this particular setting of D, my variance, my degree, I'll get a smallest possible error on my validation set, and then therefore I have a good idea that this degree is the best possible, and then I'm going to actually use it on my test set afterwards. So these plots, in addition to the ones we saw earlier, sort of capture the overall idea of bias and variance for supervised learning. Right? So we told a kind of a complete story. We've kind of went over the same ground a few times, but I think generally this core concept in machine learning is sort of complete now. So just a bit of a beyond. This is a curiosity thing for people who want to go a bit beyond. Sometimes in models that are over-parameterized, that are too big, like large neural networks, the test error can go down, and then it can go up as the model is getting more and more complicated. The one thing we don't show here, this is where we normally end in a machine learning class. Like every machine learning class I've ever seen so far has kind of ended with this story. But I think increasingly, like, people are aware of this thing called double descent. There it is. Where actually, if you keep on making the models much, much more complicated, then, sorry about that. I'm going to just shift over, move this guy. There you go. If you keep on making these models more and more complicated, this orange curve, as complexity keeps on increasing, will go up and up and up, but eventually it'll stop going up and then start going down again. So you can somehow solve this problem by just having, like, crazily overpowered models describing our fixed set of data, right? So you don't need to necessarily change the amount of training data you have or resample. You get improvements in testing just by having crazily big models, which is a new phenomenon. You can read more about it here in this paper by Belkin et al. So in practice, I think you already know how to read this. So we have our training set size on the x-axis. We have our error on the y-axis. There's a training error and our validation error like before. If there's a small gap between training and testing, and they're both high, then this more or less is the situation where we have high bias, and we're underfitting. So remember, underfitting is like, on average, it's making big errors. This is regardless of whether it's training data or test data. So the model is too simple. There's going to be way too many errors, and then both of these are very high. So the train error is high, the test error is high, and they're both like uniformly high. If you have a large gap, so if the training error is way, way smaller than the validation error, this is sort of a symptom of high variance, which we've identified as overfitting. The model is making these crazy predictions. That's an example of overfitting. So the training error is super small. The validation error is very big. This is usually a symptom of variance, of high variance. So the model is too flexible. We didn't do regularization yet, and there we are. So yeah, validation keeps improving with more data. So if we look at these curves, then we see that the curves seem to be improving and going down and down as we increase n, and like the slope is down pretty strong. Then, well, we don't have enough data. Like, the model is capable of learning more. Like, the more data I add, the model keeps on learning something more. The errors keep on going down. So I'd like to have more data if possible, please. If the curves sort of taper off like this, you see these curves are starting to get a bit flat. As I'm increasing n, the improvement to error seems to be negligible. It seems to flatten out. Then you don't really need more data. The amount of data you have here is a good match for the model you have. There are statistical ways of measuring that. Here we're just doing a visual check, but visual checks are going to be a big part of what we do with machine learning. We're going to do experiments. We're going to plot graphs like this, and then we'll be able to tell whether or not we need more data or whether more data will be a waste of time. So this is more of a cheat sheet for you in the future, or you in your machine learning lives, your journeys. But it's related to everything we talked about a moment ago. If you have training data, high train and high validation error, and the gap between them is small, this is underfitting. If the training curves are very low and the validation error is a lot higher, so like the blue curve is very low, the orange curve is very high, this is overfitting. We're doing a great job on the training data. We're doing an awful job on the validation data. This is overfitting. We know how to solve that. If both of them are decreasing, but the validation data is still high, we don't have enough data. We try to get more data. And if both validation and training curves are both low and they're close to each other, then this is great. Where we're learning something on the training data. We have low error on training data, but we're also getting low error on held out data we've never seen before. Everything's great. We can stop tweaking, or we can go on to the next step, which is sort of responsible AI. So checking fairness, checking robustness, deriving decisions, and so on. So here's a little example with learning curves. This is a plausible decision context. So we might be doing triage planning for a diabetes clinic. So we want to predict a progression score in the clinic, and we want to do some triaging. So we want to do some kind of classification and give the limited resources to some patients and triage the others. So we're going to care about a mean absolute error. So large errors are going to translate into misallocated follow-up intensities. So we've talked before about the difference between mean squared error and mean absolute error, rather. So we use that mean absolute error here. This code will jump ahead again. So like a lot of machine learning is sort of intricately, everything's kind of bundled up together. So it's impossible to have everything entirely linearized. So there's a couple of things here that are from the future. We're doing things like scaling, and we're doing different kinds of regression and different kinds of regression referring to regularization. So there's a little bit going on here which is beyond this module for now, but we'll catch up in a moment. But you can see other things that are going on are that we're using k-fold cross-validation from the previous module. Here I'm loading in a real data set, so we're not going to make a fictional one now. I think increasingly we'll start using real data sets. So sklearn has a subsection called data sets, and one of those data sets is called diabetes, so we'll just go ahead and load that data set. Here, getting all of our x's and our predictions y. We have a 5-fold cross-validation with shuffling and so on. The models themselves take advantage of some topics that we're going to be dealing with later. So ridge regression is something that comes up a bit later. And then we just plot our predictions. So for the time being, you can just view these curves as the performance you get on different models. We have a linear model and its performance on the validation, like our test data in blue. We have a ridge regression model in orange. And we have our polynomial of degree 2 plus some extra component, which is green. Again, the details don't matter right now. This is just like 3 different architectures, 3 different types of predictions we're making. And we can see in this little experiment, we change the training set size, and we see what happens, and we can see some interesting patterns. First of all, in general, the architecture that works the best, the approach that works the best, is ridge regression with an alpha equal to 5. Like that gives us, for every setting of training set size, this seems to give us the lowest error. Maybe for super big training set sizes, this difference kind of disappears, but generally, ridge seems to be the best model. So we wanted to hold one model up as a champion. That's it. We also see, there's this general behavior. across all of these approaches, if you increase the amount of training data you have, the error you get on the validation, the held out validation error, will go down. So you make better and better predictions on held out data if you have more and more training data. And the difference between these models is bigger when the amount of data is small. So if you're sitting there in a clinic and you can say we only have 100 samples, then you can say, well, definitely don't use poly 2 plus ridge, because I know how bad that is, how big this difference is in terms of validation error. But if you have like hundreds or thousands of samples, then maybe your decision to use one architecture or the other might depend on something else, how robust it is, how expensive it is to run, and so on. So just a bit of an ethics nudge as usual. I think this is increasingly important in machine learning. High variance models can produce very unstable subgroup performance, right? If all of your predictions are tight, your variance is small, then we don't expect to be very much of a difference between one subpopulation and another. But if you have high variance models, then the subgroup performance can also vary greatly. Okay, so consider that. Consider the idea that if you simply collect more data, that was framed as a solution a few moments ago, but actually collecting more data can be problematic. It can worsen privacy risks. If you go out and collect data from people, it's always a bit of a challenge in terms of privacy. It could also entrench systematic bias. If you do data collection in a way that's not sensitive, like you only collect data from Halifax or from people with a university education, et cetera, then the type of data you get is going to be very skewed, it's going to be very different. So it's not always going to be a solution in the real world. And similarly, there's just to hammer this home, a single metric like mean absolute error or mean squared error will also hide details about who the model fails on. Here's your quick check as usual. This is a simple one, I think. So hopefully you all do well on this. And here are the references. Thanks very much, and see you next time.